Okay, 1, 2, you, and you. Let's talk it through and then look at inclines. Otto? Nice. Anyone else down there with you? On the way up? Okay. Cool. Okay, let's take a look at this. Elevators at rest. I'll just toss this on the screen. This is what was discussed last semester. Comments, questions. Here's the first 6 questions. Compare what you got with what was this. Yeah, last semester I taught a Physics 11. These are the answers that they came up with last semester. Sorry? Emma, was that a question for me? Comment for me? Okay. This was the homework you guys had for last week. Here's the first half. Comments, questions, concerns. I mean, you could have interpreted some of these questions. You could answer them in different ways. This is just how it was answered last semester. I know last week Kai discussed this as instead of following it last time, he talked about an increased acceleration. That's one way to think about this too. If you let go of the apple as like the instant the elevator starts to accelerate upwards, I mean, the apple is going to fall down with the acceleration due to gravity, but the floor is going to accelerate up at it at, what was it, 2 meters per second? So you're going to see the apple fall towards the floor of the elevator at an increased rate or an increased acceleration. We will get to part F. There was a significant amount of debate regarding part F from that back table last week. Okay, if there's no questions on the top part, here's the bottom part. Questions part D through part F. Decreased acceleration. So part D, the scale would read if it slows down while you're going up. The scale is going to read a lesser mass because it's going to have a lesser normal force. The rate at which the apple will fall will decrease. Or if it speeds up while you're going down, same results. D and E are the same. And then part F, the elevator cable snaps with you inside and begins to fall. Perhaps you only have one last time for one more observation because that's what you would do. If you're plummeting to your death in a falling elevator, there's nothing else to do. You're not going to have time to make a phone call, so you may as well try and wrap your head around what's going on. You would end up in free fall with the scale, with the elevator, and you just kind of all barreling towards the ground with the same acceleration. As a result, the scale shouldn't read anything. And the apple should just float in the air beside you as you let it go as the cable snaps. I don't know if that answers any of your questions, Brad. You just said, what about the last one? This is good? Okay. When things are in free fall, I mean, weird things happen during free fall. Let's see if I have that jug. Show you guys. I'll show you guys here in free fall. Do I have the jug? Yes. Okay. I will be back momentarily, and I'll show you what I mean about weird things happening during free fall. Hey.
Oh, yeah. Oh, I thought he died. Because Isaac was like, he killed himself. Look at the toothbrush. I searched that with ChatGPT. No, I didn't. I don't know. Today was a scarf. Is he actually in jail?
Okay, so here's weird free fall. Let me demonstrate something for you guys. So I've got a jug, a 2-liter jug here. And I punched some holes into it. I need to find a part of the room that I can afford to make a mess in later. Let's go back here. Okay. So if I can get you guys to take a gander back here. Okay, so I got a jug of water. I punched a bunch of holes in this thing. When I turn this thing upright, what do you expect to happen? You expect water to come dripping out, just show you that I'm not full of it. There it is, there's water dripping out of it. To show you what, like, the weirdness of free fall, if I turn this thing upright and it starts to spit water again, and then I drop it, what's going to happen? What do you think is going to happen? You expect the water to stop pouring out, sorry? Why? Why is that what you why is that what you expect to happen? Just because it was pouring out before, and so something different must happen when I drop the thing? An idea? Does anyone have a good reason for why they think the water might stop, or does someone think different? Yeah. Because the air might push against the water. Okay. Well, this is a lot less fun than you guys. I saw this done for the first time. I was at a physics teachers conference, and I saw this thing done, and the number of adult physics teachers in the room who got this wrong, because it goes against their intuition, was pretty impressive. Here we go. It spits water, and when I drop the thing, nothing happens until it hits. You saw it stop, yeah? Yeah? And then it hits the ground, and I would go water. So in free fall, weird stuff happens.
Is it because the water and the bottle are falling together?
Is it because what?
The water and the bottle are falling together?
Yeah, it's because the water and the bottle are falling together. The reason that when you hold it there, the water is being drawn out is because gravity acts on all of them, but I've restricted the movement of the bottle. Gravity is free to pull the water out of the hole, and so that's what's going to happen. The mass of the water above pushes on the water below. That's what pressure is. And then as careful now as you walk there. And then as the water flows out, the pressure decreases, the drips will slow down. But when you let the thing go, because the water and the jug are falling together, there's no reason for the water to leave the holes. Because the weight of the water and the weight of the thing containing it are all kind of falling together. And then the thing hits the ground and starts leaking again. And then my bottle breaks open because I've done the demonstration just a few too many times. So weird stuff, counterintuitive stuff happens during free fall. So that's the elevator problem and problems like it. We're going to look at one more style of problem today before we launch into momentum. Momentum is kind of its own sort of weird thing. So we'll look at momentum later this week. But today, we're going to look at inclines. Someone steal Raina's desk because she's not here. We have a ball. The ball sits on the desk. The ball does not move. Why does the ball not move? Because why? Right, I'll tell you an answer again. Why is the ball not moving? Is that true? There is no force acting on it. There's no weirdly directional force acting on it. Because what forces are acting on it? Gravity down and normal force up. They're equal and they're opposite because this is level. And I repeatedly say this, like things, when they're level, the normal force is perpendicular to the surface, and I keep making that comment. Now we're going to take the surface and we're going to define it. The normal force is still going to remain perpendicular to the surface, but now perpendicular to the surface is which way? That way. Gravity is going to act which way? Straight down. So gravity is going to act straight down towards the center of the Earth. Normal force is going to go up this way. So when I let go of the ball, what's going to happen? It's going to roll. Because now all of a sudden, the forces aren't equal and opposite anymore. Here, the table is flat, goes up, goes down, nothing's happening. But as soon as I angle the thing, we can start to split these forces up. The normal force is up this way. When I let go of the ball, does it launch off the incline? No. So why does the ball roll down the incline? Because gravity is dragging it down. And we can break up the effect of gravity. You betcha. Gravity's pulling, because gravity doesn't pull down the incline. Gravity pulls straight down. But that downward pull of gravity has two effects. A portion of gravity pulling down is why the ball stays on the incline. Yeah? But that's not all of it, because, normal force is up. So there needs to be a portion of gravity opposite normal force. Because it's not being launched up, it's not being sucked into the incline. There has to be a balance there between an angled normal force and a portion of gravity. But when I let go of this thing, it's going to roll down the incline. So something has to be dragging it that way. Otherwise, Laughlin doesn't make sense. So, let's draw it out. Okay, so ball sitting on a level surface will not roll because the forces on it are balanced. F net equals 0. We've got an Fn up and an Fg down, and those are equal and opposite. The thing isn't going to move. But when we take that same thing and we throw it on an incline, I'll draw what we were talking about here, the tennis ball on the inclined desk. The normal force is going to be perpendicular to the surface. There's our Fn. Fg is always going to be straight down. That never changes. And yet somehow this ball doesn't get launched off the incline. It doesn't get sucked into the table. It slides down or rolls down the incline. So we have to be able to figure out what's happening here. Kale and Brad, are we figuring stuff out? We're arguing about something. This is great. Perpendicular. Is that true?
No, I don't.
Okay, so again, an important thing to remember, Fg pulls straight down at all times. Fg is always towards the center of the Earth. It's always, always, always straight down. And so how you draw this is important. Don't get sloppy here. Fn is always 90 degrees to or perpendicular to or in math, the notation for this is this, perpendicular to the surface. And so we have something that looks like that, where this is 90 degrees to the surface. And so what we're going to start to do is we're going to start to break this thing up. We have to figure out what is actually acting. And so let's draw it again. I'll grab another color. Grab a light gray here. And feel free to make this biggish. We've got an FG and an FN. Those are the forces. If you were asked to draw a free body diagram, that's it. The free body diagram is done. But there's something here that we can do now. These are the only forces, but especially this FG. FN is just doing what it always does. It acts normal to the surface. It's the reason why this object doesn't fall into the surface, but it's not so big that it launches the thing off the surface, because that would be weird. If you just put your pen down in your desk, started launching it into the air, that would be concerning, as it should be. So what's actually happening here? It means that when gravity is, when you incline something, it means that the gravity force that was acting purely downwards is no longer just acting straight down anymore. It's got a portion of gravity that looks like this, and be deliberate about how you draw this. I'll zoom this in so you can see what I'm doing. This portion of gravity is going to be the same as Fn. I'm going to call this Fg perpendicular is the notation I'm going to use for this. And we know this has to be there because, again, Fn isn't launching things up into the sky, and gravity's not making the thing suck into the surface, so there has to be a piece of gravity that is equal to all of Fn. These two need to be equal. But the thing is sliding down the incline. So then there also needs to be a portion of gravity that is in the same direction as the incline itself. I'm going to call this thing Fg parallel. And this is this notation I'm going to use for parallel. It's the two parallel lines. It looks like FG11. It's not. That means Fg parallel. And this thing is always going to be parallel to this incline here. So label some of what I've said. These two have to be, Fn and Fg parallel have to be equal. And so what I've just done here is I've taken Fg and I've broken it up. Brown. Something we haven't looked at yet because we've stayed largely in one dimension is the idea that vectors themselves can be broken into what are called components. So what I've done is I've taken Fg and I've said, okay, well, gravity has, the gravity that's acting straight down is having two effects here. It's one of the effects of gravity is that Fn and Fg perpendicular have to be equal to each other. And the remaining portion of gravity is the thing that's dragging this thing down here. What is interesting about Fg perpendicular and Fg parallel? If Fg perpendicular is equal to and opposite Fn, what does that tell us about these two blue vectors here, or the components of these two, or these two blue components here? What is true about how these two things have to meet? Okay. My question was, how are these two blue components of gravity related to each other? Sorry? This one, neither of them go down in the traditional sense of the word down. They're not the same. We know Fn and FG perpendicular have to be the same. They have to be equal and they have to be opposite. So if Fn is, Fn is called Fn because it's a normal force. Normal means perpendicular in math. So Fn is perpendicular to the incline. So then FG perpendicular also has to be perpendicular to, that's why it's called FG perpendicular. It means it's perpendicular to the incline, which means it meets the incline at 90 degrees. And FG parallel is called FG parallel because it's parallel with the incline. And so the angle between these two vector components has to be 90 degrees. Vectors can be broken into components that are perpendicular to each other, which is an important detail. Because if they're perpendicular to each other, what can we do with this fancy triangle here? If that's a right angle triangle, what tools become available to us? Trig. All of trig becomes available to us. So, Ka and Toa now all of a sudden become available to us. We can start to figure out how we know these two can't be, well, maybe they can. They might be equal to each other. We don't know. But we know that because they're meeting at right angles to each other, this is a right angle triangle. This force FG forms what side of this triangle? What is the side called that's across from the 90? It's the hypotenuse. So this guy here is going to be the hypotenuse, that guy, of that right angle triangle. Let's zoom this thing back in here a little bit more. In order to solve this thing, we're going to know what FG is because presumably they'll give us the mass. We need one more piece of information. If we know FG, and we know that this is a right angle triangle, and if I want to find FG perpendicular and FG parallel, what one more piece of information do I need to be able to use trigonometry to solve this triangle? Yes, Ezra, I need an angle. If I knew what angle the incline was, I'd be able to determine what angle, an angle in this triangle. They've taken angles largely, angle relations out of math largely. I think Foundations 11 does them, where you look at parallel lines and alternate interior angles and co-interior angles and all this kind of thing. But lots of students who take Physics 11 are in Pre-Calc 11, not necessarily Foundations 11. So we lose all of that. And so there's a few ways I can argue this, but I'm going to make an argument for you here. If I took, this is the way physicists like to make these kinds of arguments. There's a nice, rigorous mathematical way for me to argue what I'm about to argue, but there's also kind of a physicsy, hand-wavy argument, and that's the one that I'm going to make. Are we cool with the diagram the way I've drawn it? You guys understand that all of the pieces we're comfortable with it? Colton says thumbs up, cool, Colton, you're on the spot. We want to make an argument. Thank you for responding so vigorously. I love it. We want to figure out what angle this aligns with in this little triangle here. Colton, does your gut tell you anything about how what angle in that triangle could be related to the angle of the incline? What does your gut tell you? I don't care if the answer is right or wrong. What does your gut say? Or yes, it's 50.
It's the triangle that with all the degrees out.
Mm-hmm.
So,
this is going to be 90 here. So we can find that. But that's not going to help you. there needs to be a relationship. There needs to be a nice relationship between the angle of the incline and either this angle here or this angle here in this triangle. Right.
The angle that you have for the triangle that's on.
Yep.
That would directly affect like the angle for like FG perpendicular.
So you're arguing this angle here? I think that's telling you?
Yeah.
Why do you want to say that? Emma? Why is it bottom? Okay. So Brad's gut and your gut are clearly in opposition to each other. So here's my physicsy hand wavy argument here. This incline exists. We'd set it up to look like this. Actually, I'll grab some pens because that'll make my life a little bit easier. I've got a normal force straight up, and I've got an FG straight down. As I incline this, those of you who can see what's going on here, I've got a normal force up at an angle. I've got FG straight down. You're going to have to kind of imagine that I've got a perpendicular component of gravity acting that way, and I have a parallel component of gravity acting that way. Those of you who can see what I'm doing, we cool with that? As I decrease the incline, what two things come together? Or if we look at this picture here, as I close this incline, and this angle reaches 0, what two lines overlap in that triangle?
Does the FG line through FG perpendicular aligns with the normal FG?
Yeah, as I close these two, this thing closes. If I were to open this incline up all of the way, take my incline, and I open it up all the way, my normal force is going to be there, gravity is going to be there. If my incline is 90 degrees, Fn and Fg are also going to be 90 degrees to each other. As I crank this thing up, this angle is going to get larger and larger too. There are mathematical angle relationships that I could show you, but I'm hoping that I'm able to convince you with my physicsy hand wavy argument here. As this thing closes, so does this one. As this thing opens, so does that one. And they have to open and close together in equal measure. So what that means is, that top angle there, Brad, you were right, that top angle there and the angle of the incline are the two that have to be equal to each other. This guy here and that guy there, these two angles are equal. And because we've got these pieces, now we can go ahead and we can start to find some of these angle relationships. For the sake of saving you guys some work in the future, as you do some of these questions, and to review a little bit of your trig, I'm going to give you guys expressions for FG parallel and FG perpendicular right now. If this is the angle up here that we're using, I'm going to call it theta because it is theta. These two angles are the same. If we know the mass of this block, we know the force of gravity. Fg is just mg, mass times 9.8. And so I can start to use, and so that'll be the hypotenuse of this triangle. If I know the hypotenuse and I know this angle, we can use trig relationships to find the perpendicular and the parallel component of gravity. So it doesn't matter which one we find first. Let's do, what did I do first last semester? I did FG parallel first last semester, so let's do that one here. Right, small, leave some space. I want to find an expression for FG parallel first. FG parallel is this guy down here. what is this side compared to that angle? How would we name this side in the right angle triangle? It's opposite. It's across the triangle from the angle that we've got. So this guy here is opposite. And I know the hypotenuse. So if I've got hypotenuse and I'm looking for the opposite, which trig ratio am I going to use? I'm going to use SO. That's the point of SOHCAHTOA. O stands for opposite, H stands for hypotenuse. This is what I'm looking for. This is what I know. So we're going to use sine. So how we use this is we say that the sine of our angle theta is going to be equal to the opposite side, which we've called FG parallel, divided by the hypotenuse FG. And I want to figure out what FG parallel is. How do I solve this expression for FG parallel? To get it alone, what do I have to do? Basic algebra. If I want to solve this expression for the numerator, how do I get the numerator alone? I'm already dividing FG. Because I'm dividing by FG, I want to get rid of it. I want to move it to the other side. So I want to multiply FG onto both sides. And so what we're going to get here is that FG parallel is going to equal FG times the sine of theta. For all time, that's what we're going to get. And that's a lowercase g, not a 9. If I go ahead and do the other one here now, this is a different color. It's pink. If I want to find FG perpendicular, this side here, how is this side here related to that angle there? That's the hypotenuse, that's opposite, so this side must be adjacent. I'm hearing some whispers. So if this is adjacent and this is hypotenuse, which of these trig ratios are we going to use? We use cosine. So if I want to find FG perpendicular is going to be the cos of that angle up top there, theta, is going to equal FG perpendicular, the adjacent side divided by the hypotenuse, FG. So then, if I'm going to solve this thing for FG perpendicular, I'll just go down here. FG perpendicular is going to equal, how do I get it by itself? It's the same procedure. I want to get rid of the denominator. So to get the numerator by itself, what do? Multiply both sides by the denominator. So this guy's going to be FG cos theta. And if you memorize these two relationships, you can use them forever. You can rederive them every time. If your trig is good, there's no reason why you can't. But if your trig is sketchy and you just want to take my word for it, then commit these two expressions to memory. They will always be true. Questions, comments, concerns about what I've just done? I can never tell if you guys are arguing about what I'm doing or if you're arguing about mocking each other. Okay, two important things to notice. Only the parallel component pulls down the ramp. So the only thing that has any effect on how the thing slides down the ramp is FG parallel. And the perpendicular component, the only reason it exists is because it's equal to and opposite Fn. And so we can start to use some of these relationships here to solve. I'll go through 3 examples for you, and then you'll be free to practice. Okay. Stop me if there's any confusion, any doubt. Okay, then let's go. 3 examples. We've got an 8-kilogram block. It slides down a frictionless inclined plane as shown. What's its acceleration? Okay, free body diagram. What forces are acting on the block? Fn. Fn, remember, perpendicular always to the surface. And now that means it's off at an angle there. What other force is acting on this thing? Fg. Fg is always straight down. And I would encourage you, draw them big so that you can comfortably draw your component triangle and you're not crammed for space. So if this is how it's set up, if Fg is straight down and Fn's up there at an angle, as soon as you incline this thing, what you want to do is you want to break Fg up into components. These components are going to meet at a right angle to each other. One of them is going to be parallel to the incline, and the other one of them is going to be perpendicular to the incline. And I have students every semester ask me, do I have to be careful how I draw these things? Does it matter how close I am? Yeah. Take your time to get good. You need to draw these things as accurately as you possibly can so that your intuition isn't competing with the drawing that you've done. If you make it harder on yourself to visualize this, then you're screwed. This is the angle of the incline. That's 35 degrees. And I'm hoping I have successfully convinced you that if this angle is 35 degrees, then this one here must be 35 degrees as well. And so that's the picture. We can now go ahead and we can fill in some of this information. We know Fg. Fg is going to be the mass of the block times 9.8. Fg is always equal to, again, unless you're in orbit somewhere using universal gravitation, Fg is just going to equal little m times little g. So that's just going to be 8 times 9.8. Which is what? 8 times 9. 8 times 9.8. 78.4. And we're asked to find the acceleration. Are there any other forces acting on this thing? Sorry? Is there friction acting in the question? Why not? Because it says frictionless. Thank you for demonstrating exactly what I was hoping someone would demonstrate. I'm sorry it was you. It had to be someone. I would be sorry, it doesn't matter who it was. Someone had to speak up. There is no friction. It's frictionless. So let's set this up. We're in dynamics, so everything starts with F net equals ma. When the block gets released, it's going to slide down the incline. So what forces or pieces of forces are going to show up in the F net equation? What causes this thing to move? Is it all of gravity, or is it a component of gravity? Which way does the block move? Down, or? So it's not perpendicular. It's not down. It's down. So it's going to slide down the incline. Are there what forces or what arrows have I drawn on this page act in that direction? Act down the incline. Fg parallel. That's the only one. This one doesn't move, or this one doesn't act in the direction of motion. This one's not acting in the direction of motion. This one's not acting in the direction of motion. It's only the one parallel to the incline. So this guy here, Fg parallel, is the only one that's going to be included in this F net equation. So FG parallel is going to equal MA. And now I can start to plug these things in. FG parallel is opposite the angle that we've been given. So it's going to be sine. That guy there is opposite. So if we're using SOHCAHTOA, this is the opposite side. We know the hypotenuse. We're going to use sine. So FG parallel, I can swap out for FG sine theta equals MA. This is the expression that we came up with up here for FG parallel. FG parallel is FG sine theta, so we replaced it. FG sine theta equals MA, so now I can start to plug in values. FG is 78.4 times the sine of what angle? Times the sine of the angle 35 degrees is equal to the mass of our object 8 times the acceleration A, and now I can go ahead and solve this thing. To get the acceleration by itself, I'm going to divide by 8. And we're going to get that the acceleration down the incline is what? What is 78.4 times the sine of 35 divided by 8? For those of you it's been a while since you've done trig, grab your calculators and punch this thing in. If you're in math right now, make sure your calculator is in degrees, not radians. That's going to be something that Kai, where are you, Kai, hopefully watching this video, needs to be aware of.
44.96 or 97.
Did you divide by 8?
Oh, no.
Sorry? 5.6 meters per second squared. And it needs a direction. What's the direction now? The direction is weird. But we can use the objects in the picture to give us the direction. If you had to describe which way the block was accelerating, well, what would you say? Sort of. You don't have to get quite that exact. Down the slope. You bet. Questions, comments, concerned about what we've just done? How you doing, Dwayne? Because I just heard you say something. And you gave me a look a second ago. Perfect. That's why I asked how you were doing, because I couldn't quite hear what you said. Love it. Okay. It's not always you, Dwayne. It was just you this time. Okay, here we go. Next one. If there is, I'm going to keep going unless somebody stops me. How much force is required to push an 11 kilogram block up the frictionless ramp shown at a constant velocity? Okay, forces, what are they? Anybody? Give me a force acting in this problem. Normal. Normal is perpendicular to the incline. It's going to be up that way somewhere. Cool. What else is acting? Gravity, and gravity always acts straight down. Make them big. Are there any other forces acting in the problem? Okay, so you want to careful. We're just doing the free body diagram now, and then we'll break stuff up into components. Are there any other forces acting in the problem? There's an applied force. Applied force is acting which way? Up the incline. Cool. Where did that come from, Emma? That. Yep. How much force is required to push an 11 kilogram block up the incline? So there it is. Those are all of the forces. It's frictionless again. It won't always be, but it is now. So now, Brad, at this stage, free body diagram is done. Now we're going to break up FG. FG has a component that is perpendicular to the incline, and it has a component that's parallel to the incline. If this angle right here is 58 degrees, then that angle here is going to be 58 degrees. We could find FG. FG is just going to equal m times g, and we know the mass of the block is 11. So that's just going to be 11 times 9.8. 11 times 9.8 is something. 107.8. And now, because this is a dynamics unit, we're going to look at F net equals MA, but I'm not going to write down F net equals MA because there's something significant in the problem that's going to solve us or save us some work. There's a significant piece of information that we haven't mentioned yet. What is significant about the way the question is worded? Sorry? Constant velocity. What does constant velocity imply? Sorry? What's zero? Acceleration. Constant velocity means the acceleration equals 0. Which means when I set up my F net equation, F net is going to equal 0. What then is implied? If there is no net force acting on this object, all of the forces must be, they have an equal partner, an equal and opposite partner. Fn is equal to an opposite Fg perpendicular, but that doesn't help us. What is Fa equal to an opposite? The parallel component. So now we know Fa is going to equal Fg parallel because the constant velocity, acceleration is 0. Acceleration is 0, F net is 0. F net is 0, every force has an equal pair or partner. And so now this is easy to solve. We have an expression for Fg parallel already. Fg parallel is equal to Fg sine theta. So then Fa is just going to equal Fg sine theta. All of this follows logically. So I can just plug this thing in. Fa is going to equal Fg is 107.8 times the sine of something, 58 degrees. Okay. You might be. You are leaving. Okay. So you're not might be. You definitely are leaving. Have a good day. Watch the rest of the video. So then what's Fa? What is the applied force required to keep this thing moving up the ramp at constant velocity? Got a value, Cal? Really? It's different than what I got. It's close, but it's different. That's what I got. 91.4 newtons. There it is. Comments, questions, concerns about what I've done? If not, I've got one more example for you, and then you're on your own. Okay, last one. Let's bring friction in, because why the heck not? I want to make two changes here, actually. We're going to get rid of the mass. And I want to show you something cool. A block sits on an inclined ramp whose coefficient of friction is 0.12. Sorry, 0.21. We want to find the acceleration of the block. Okay, cool. So, free body diagram. What forces are acting which way? Rattle them off. The longer this takes, the less time you have to practice. Sorry? Fn. Which way? Up? So perpendicular. There's Fn. Next one. Gravity, straight down. I want to make it big because it's going to be needed. What other forces are acting? Yes, Dwayne, friction. Which way is friction going to act? Opposite the block. Block wants to slide down, friction's going to go up. You betcha. Cool. I got a force of friction. And that's it. There's nothing else here about an applied force. We just got a block now. It's going to sit on a friction-y surface, and it's going to slide, and we want to find the acceleration. So now we're going to add the component triangle in here. That guy's going to go that way. That guy's going to go this way. This is FG parallel. This is that. Nope, I lied. That's perpendicular. This one's FG parallel. And now we can start to fill this thing in. We don't know the mass. I took it away. It's not 15 anymore. It's gone. So if you don't know the mass of something, give it a name. What is a totally reasonable letter to use for the mass? M. Yes. Thank you. So mass is M. So this thing, Fg, is just going to be mg. I took it away to prove a point. I want to show you something cool. So Fg is going to be equal to mg. What else can we do with this? I've got a force of friction here now, and all I know about the force of friction is that there's a coefficient of friction. What's the formula for the friction? Force of friction is equal to Fn times mu. Force of friction is equal to mu times Fn. Okay, cool. So now I need to find Fn. Because up until this point, friction hasn't been here. We don't care about Fn, but now we do. So what's Fn going to be equal to? Let's go through the steps. Fn is equal to what? What is its equal and opposite partner? All of gravity? Now, if this was a flat surface, Fn and Fg would be equal. But it's not. It's inclined. So Fn is not going to be equal to Fg. It's going to be equal to Fg perpendicular, this piece. So Fn is going to equal Fg perpendicular. And we have an expression for Fg perpendicular. Fg perpendicular was just equal to Fg cos theta. That's this guy right here. And Fg, we don't have the mass, so Fg is just going to equal mg for the time being. So Fn is going to equal mg cos theta. So the force of friction then is just going to equal mu times mg cos theta. So then this expression is going to become mu times mg cos theta. Cool. Let's set up our equation. We want to find the block's acceleration. To find the block's acceleration, we're going to set up F net equals ma. What forces are acting in the direction of motion of our block? friction and parallel. Which way do you want to call positive? Now that we've got equal and opposite, we need a direction to be positive. Which way? Down the incline. Okay. We're going to call this way positive. So when I set up my F net equation, it's going to be all the positive forces minus the negative forces. So we're going to have this guy's acting in the direction that KL decided was positive. So we're going to have FG parallel minus the force of friction is going to equal MA. We have expressions for all these things. FG parallel, we said before, was FG sine theta. So we're going to have, and FG is just MG. So we're going to have FG sine theta minus MG cos theta equals MA. I can start to plug some things in here. We said that FG was just MG. So I'm going to have an MG sine theta minus MG cos theta equals MA. For those of you who are mathematically inclined, which is all of you, because you're in a Physics 11 course, what cool thing can we do here right now? Emma? You had a guess, though? I'll take a guess. You're scared of guessing because you were wrong earlier? I feel that. Oh, sorry. What can I cancel, Dwayne? All the M's, not the G's. Because I have a G just in these two, but I don't have a G over here. But I've got an M here, I've got an M here, and I've got an M here. I can divide every term by M. So because I can divide every term by M, divide by M, divide by M, divide by M. Cancel, cancel, cancel. What I wanted to show you in this question is it doesn't actually matter what the mass of the block is on the incline. If you know the coefficient of friction, that will be true for any object mass. It could be me standing on a roof. It could be my daughter standing on the roof right beside me. As long as we're wearing the exact same boots with the exact same coefficient between us and the incline, we will slide together, which is weird. But that's the physics. So this is going to be, now let's fill everything in. G is 9.8. So we're going to get 9.8 times the sine of this angle here, which is 40 degrees. 9.8 sine 40 minus 9.8 cos 40 equals A. The masses are gone. So what's the acceleration for every object with the same coefficient of friction on that incline? A equals what value? As soon as you got a value, tell me what it is, for the sake of time. Minute, you got a value? Try again. Oops, we forgot something. Ah! Nobody caught me. What did I leave off? I left off a mu. There should be a mu there, and there should be a mu there. So this isn't 9.8 cos 40, it's 9.8 cos 40 times 0.21. Oh, delete off. Figure yourself out. So 9.8 times the sine of 40 minus 9.8 times the cosine of 40 times 0.21. 4.72 meters per second squared down the slope. There it is. Inclines. Not bad, but different. Okay, you need to play. If you don't play, you'll never retain anything we've just talked about. So, flip the page. There are 9 questions, and you're going to do 6 of them. I want you to take a look at the following questions. You've got a little bit of time now. You're going to have some homework tonight. 1, 2, 5, 7, 8, and 9. And I will tell you, One of those 6 questions is going to show up on your unit test. I will not tell you which, but one of those 6 questions is on your test for this unit. 1, 2, 5, 7, 8, and 9. Make sure you got it all. All the edges, okay? Okay, use what time you've got. Yes, you may. Good luck. May the force be with you. Get going. One of those questions will be on your unit tests. Oh, apparently you guys will be back, the ceramic students. You're going to be back around 1 on Wednesday. Well, you leave at 9:30, and you'll be back around 1. So you'll be here for my block. You have me first block. Oh, wait a sec. You guys have this test first block. I either have to make it shorter, or you guys are going to have to come here early. Or I can move it to Thursday, and then you get lunchtime. But how many of you guys would actually come at lunchtime? When I'd offered it last time, you guys didn't take me up on it. And you got screwed. First period physics test. That's, it almost feels unkind. Okay.